For centuries, humanity has dreamed of reaching other worlds, not just visiting them, but walking on their surfaces, breathing their air, building something that lasts. And today, we are closer to that dream than ever before. We have sent probes to the edges of the solar system. We have landed machines on Mars. We have flown spacecraft past Pluto and beyond. And with powerful telescopes, we have begun to discover planets orbiting distant stars, worlds that, at first glance, seem almost Earth-like. Two of these worlds have captured the imagination of scientists and dreamers alike. One is Titan, a moon of Saturn, shrouded in thick orange clouds with rivers, lakes, and seas, though not made of water, but liquid methane. The other is TRAPPIST-1e, a rocky planet orbiting a dim red star located in the habitable zone, where temperatures might allow liquid water to exist. At first, these places sound like destinations, future colonies, new frontiers, second homes for humanity. But the reality is far more complicated, because when scientists study these worlds closely, when they calculate the distances, the environments, the physics, and the limits of technology, a sobering truth emerges. Reaching these worlds is not just difficult, it may be nearly impossible, at least for now. Not because of a single obstacle, but because of many. Distances so vast that travel would take decades or centuries. Environments so hostile that human survival becomes almost unimaginable. Energy requirements that stretch the limits of what our civilization can produce. And even deeper than that, there are limits imposed not by engineering, but by the laws of physics themselves. Tonight, we will explore why worlds like Titan and TRAPPIST-1e, despite appearing within reach in our imaginations, remain far beyond our grasp. We will look at the true scale of space, the hidden dangers of deep space travel, the challenges of surviving on alien worlds, and the quiet, humbling reasons why the universe is not easily conquered. This is not a story about giving up. It is a story about understanding reality as it truly is. Because sometimes the most fascinating discoveries are not about what we can do, but about what we cannot. And as we begin this journey, one realization will slowly become clear. The universe is full of worlds, but reaching them is another matter entirely. At first glance, Titan appears almost inviting. Among all the worlds in the solar system, it is one of the few places that seems, in certain ways, strangely familiar. It has clouds, it has weather, it has rivers and lakes. It even has dunes shaped by wind and seasons that change over time. From a distance, Titan does not look like a barren rock. It looks alive, and that appearance has fascinated scientists for decades. Titan is Saturn's largest moon, and it is enormous, larger than the planet Mercury. For many years, its surface remained hidden beneath a dense orange haze, impossible to see clearly from Earth. But in 2005, the Cassini-Huygens mission changed everything. A small probe named Huygens descended through Titan's atmosphere, slowly drifting downward for more than 2 hours. As it fell, it transmitted images back to Earth, images that showed landscapes unlike anything ever seen beyond our planet. Channels carved into the surface, rounded stones shaped by flowing liquid, flat plains and distant hills. It looked uncannily like a cold, alien version of Earth. But the similarities were deceptive, because what flows across Titan's surface is not water. It is methane and ethane, hydrocarbons that exist as gases on Earth, but as liquids in Titan's extreme cold. The temperature on Titan's surface is about minus 179 degrees Celsius, cold enough that water becomes as hard as rock, cold enough that ordinary materials behave in unfamiliar ways, cold enough that exposed human tissue would freeze almost instantly. At such temperatures, survival without protection is impossible. Even the most advanced spacesuits ever designed have never been tested in conditions that cold for extended periods, and temperature is only the first obstacle. Titan's atmosphere, although thick, is unbreathable. It is composed mostly of nitrogen, with methane and trace gases mixed in. There is almost no oxygen. A human standing on Titan would suffocate within minutes without a life support system. But strangely, Titan's atmosphere is also one of the few things that makes it seem appealing, because it offers protection. Unlike the Moon or Mars, Titan's thick atmosphere shields the surface from radiation. Solar and cosmic radiation that would damage human cells is largely absorbed before reaching the ground. In that sense, Titan is safer than many other worlds. Yet the same atmosphere that protects also creates problems. It is dense and hazy, reducing sunlight to a dim orange twilight even at midday. The sun, so bright and powerful on Earth, appears on Titan as a faint disk in a dark sky. Solar power becomes inefficient. Visibility becomes limited. Psychological effects of living in permanent dimness could be severe. Even the passage of time would feel different. A day on Titan, one full rotation, is about 16 Earth days. But Titan orbits Saturn, and its seasons last more than 7 Earth years each. Imagine living in a place where winter lasts for years, where the sky never truly brightens, and where the landscape remains locked in freezing cold without relief. And yet, despite these conditions, some scientists believe Titan may be one of the most interesting places in the solar system for studying life. Not life as we know it, but life as it could be, because Titan possesses complex organic chemistry. Its atmosphere contains molecules that resemble the building blocks of life. Some researchers speculate that exotic forms of life, perhaps based on methane instead of water, could exist in Titan's lakes. This possibility makes Titan scientifically priceless. But scientific interest does not make it easy to reach. Titan lies nearly 1.4 billion kilometers from Earth. Even traveling at tens of thousands of kilometers per hour, a spacecraft takes years to arrive. Cassini, for example, took nearly 7 years to reach Saturn, and that was an unmanned probe designed to operate without human needs. No oxygen, no food, no protection from long-term radiation exposure. For humans, the journey would be far more difficult. Astronauts would need shielding from cosmic radiation, which accumulates over long journeys and increases the risk of cancer and other diseases. They would need food and water for years, or reliable systems to recycle and produce them. They would need protection against psychological stress, isolation, and the effects of living in confined spaces for enormous periods of time. And perhaps most challenging of all, they would need propulsion systems far more powerful than those we currently possess. Chemical rockets, the kind used to launch spacecraft today, are not efficient enough for routine human missions to Saturn. More advanced concepts, nuclear thermal propulsion, ion drives, or even fusion engines, are still experimental or theoretical. Until propulsion improves dramatically, Sending humans to Titan remains more a dream than a plan. And even if we could send them, bringing them back would be even harder. Leaving Titan requires escaping not only Titan's gravity, but Saturn's as well. Every kilogram of fuel would need to be transported across billions of kilometers in advance, or produced on Titan itself, an enormous engineering challenge. Then there is the question of landing. Titan's thick atmosphere makes parachute landings possible, which is easier than landing on airless worlds. But its cold temperatures and hydrocarbon seas present new hazards. Landing in the wrong location could mean sinking into a methane lake. Landing near dunes could mean navigating unstable terrain. Every step would require careful planning. And even after all of this, there remains a deeper question. Why go? Titan is fascinating scientifically. It may teach us about chemistry, about planetary formation, about the origins of life. But it is not a place where humans could live easily. It is too cold, too distant, too alien. Any human presence would depend entirely on technology, sealed habitats, artificial heating, continuous life support. Remove the technology, and survival would last only minutes. This raises an important distinction. There is a difference between visiting a world and living on it. Titan may be reachable someday by explorers, but colonizing it, building cities, creating self-sustaining communities would require technology far beyond anything we possess today. And even then, the environment would remain unforgiving. Yet Titan is still within our solar system. Still, in a sense, close, because the next world in our story lies far beyond. Not billions of kilometers away, but trillions. A planet orbiting a distant star. A world that might resemble Earth in size and temperature. A world called TRAPPIST-1e. And reaching that world is not just difficult. It pushes against the very limits of physics itself. That is where the journey leads next. If Titan feels distant, TRAPPIST-1e belongs to another scale of distance entirely. It is not a moon orbiting a planet in our solar system. It is a planet orbiting another star, an entirely different sun, located about 40 light-years from Earth. 40 light-years may not sound enormous at first. In everyday terms, numbers like 40 feel manageable. But in space, that number represents something staggering. A single light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. That is nearly 10 trillion kilometers. 40 light-years is roughly 400 trillion kilometers. To understand what that means, it helps to consider how fast our fastest spacecraft actually travel. Voyager 1, the fastest human-made object ever to leave the solar system, moves at about 17 kilometers per second relative to the Sun. At that speed, reaching TRAPPIST-1e would take tens of thousands of years, not decades, not centuries. Civilizations would rise and fall before the spacecraft arrived. Even with more advanced propulsion concepts, nuclear engines or ion drives, the journey would still take many thousands of years. This is the first barrier to reaching TRAPPIST-1e, distance itself. Space is not just large, it is overwhelmingly empty. Between stars lies a vast ocean of near-perfect vacuum. No atmosphere, no sunlight strong enough to provide energy, no places to stop and refuel. A spacecraft traveling to another star must carry everything it needs from the beginning, or find ways to produce resources along the way, which introduces even more complexity. Then comes the second barrier: time. Human beings are not designed for journeys lasting centuries. Even if a spacecraft could travel for hundreds of years, the original crew would not survive to see the destination. This has led scientists and engineers to consider extreme ideas: generation ships, enormous vessels where multiple generations live and die during the journey; cryogenic sleep, placing astronauts in suspended animation, a technology that does not yet exist; robotic or AI explorers sent in place of humans. Each of these ideas introduces challenges of its own. A generation ship would need to function as a completely closed ecosystem for centuries, recycling air, water, and nutrients with perfect reliability. A single failure could be catastrophic. Cryogenic preservation remains experimental even on small biological samples. Preserving complex organisms safely for decades or centuries remains beyond our current understanding, and sending only robots, while scientifically valuable, does not fulfill the dream of human exploration. Then there is a deeper barrier: the speed of light itself. According to the laws of physics as we understand them, nothing with mass can travel faster than light. As an object accelerates toward light speed, the energy required increases dramatically, approaching infinity. This is not an engineering limitation. It is a physical one. Even reaching a fraction of light speed would require enormous amounts of energy, far beyond what humanity currently produces. Some theoretical concepts, like warp drives or wormholes, appear in physics equations, but they remain speculative, requiring exotic forms of matter or energy that have never been observed. For now, faster-than-light travel remains in the realm of theory, which means that interstellar travel is constrained by time in a way that planetary travel is not. Then comes another challenge that is often overlooked. Interstellar space is not perfectly empty. Tiny particles of dust and gas drift between stars. At ordinary speeds, these particles pose little threat, but at a significant fraction of light speed, even a grain of dust becomes dangerous. A collision at such velocities would release enormous energy, potentially damaging or destroying a spacecraft. Protecting against these impacts would require heavy shielding, which increases mass, which increases the energy required for acceleration. Every solution introduces another problem. And even if all these obstacles were overcome, if humanity somehow built a spacecraft capable of traveling to TRAPPIST-1e in a reasonable time, another question would remain. What would we find when we arrived? TRAPPIST-1e is often described as Earth-like, but that term can be misleading. It is roughly similar in size to Earth and orbits within the habitable zone of its star, where temperatures might allow liquid water to exist. But similarity in size does not guarantee similarity in conditions. TRAPPIST-1e orbits a red dwarf star, much smaller and cooler than the Sun. Red dwarfs are known for intense stellar flares, powerful bursts of radiation that could strip atmospheres from nearby planets or make their surfaces hazardous for life. The planet may be tidally locked, meaning one side permanently faces its star, while the other remains in eternal darkness. One hemisphere could be scorched, the other frozen. A narrow band between them might be temperate, but harsh and unstable. We do not yet know if TRAPPIST-1e has an atmosphere thick enough to protect life or oceans deep enough to stabilize climate. We cannot yet see its surface directly. All we know comes from tiny changes in starlight measured across vast distances. This means that even after centuries of travel, explorers might arrive at a world that is not habitable at all, a frozen desert, a barren rock, or a planet whose environment makes long-term human survival impossible. Then there is the challenge of communication. Signals traveling at the speed of light would take 40 years to reach Earth. A message sent from TRAPPIST-1e would not be answered within a human lifetime. Explorers would be truly alone, cut off from the civilization that sent them. This psychological isolation could be as difficult as the physical journey itself. And yet, despite all these challenges, the idea of reaching another star continues to inspire scientists and dreamers alike. Because interstellar travel represents more than exploration. It represents survival. Our sun will not last forever. In billions of years, it will expand, altering the solar system and eventually engulfing the inner planets. Long before that, changes in solar output may make Earth uninhabitable. On cosmic timescales, remaining confined to one star is not a permanent solution. But recognizing this does not mean we are ready to leave. Not yet. Humanity is still at the very beginning of space exploration. We have taken our first steps beyond Earth, landed robots on nearby planets, and sent probes into interstellar space. But traveling to another star with humans aboard remains far beyond our current capabilities. And perhaps that realization is itself one of the most important discoveries of all. The universe is full of worlds. But distance is not just a number. It is a barrier written into the fabric of reality. Titan challenges us with environment. TRAPPIST-1e challenges us with distance. Together, they reveal a truth that is both humbling and profound. The universe is not easily reached, and understanding that truth is the first step toward exploring it wisely. Because before we can travel to other worlds, we must first understand the limits that shape the journey. Even if humanity could overcome the distances, the energy requirements, and the physical limits of travel, another problem would still remain. One that is less obvious, but just as critical. Survival. Reaching a distant world is only the beginning. The real challenge is living there. And when scientists study Titan and TRAPPIST-1e carefully, they begin to see that these worlds are not simply far away. They are fundamentally hostile to human biology. The human body is adapted to a very narrow range of conditions. A specific temperature range, a specific atmospheric pressure, a specific gravity, a specific chemical environment. Even small deviations from these conditions begin to cause problems. This becomes clear when we consider how difficult it already is to live in extreme environments on Earth. Polar regions require specialized clothing and shelter. Deep oceans require pressurized vessels. High altitudes reduce oxygen levels and strain the body. And yet, these places are still on Earth, still within the range of environments life evolved to tolerate. Titan and TRAPPIST-1e are far beyond that range. On Titan, the temperature alone creates enormous challenges. At nearly -180 degrees Celsius, metals become brittle, lubricants freeze, and many materials lose flexibility. Machines designed for Earth must be redesigned completely to operate in such cold. For humans, the problem is even more severe. Exposure to Titan's surface conditions without protection would result in rapid freezing of skin and tissues. Breathing the atmosphere is impossible. Even simple tasks like moving, working, or repairing equipment would require heavy protective suits. But the cold is only one part of the problem. Water, which is essential for life, behaves very differently at Titan's temperatures. Liquid water cannot exist on the surface. Any water exposed to the environment freezes instantly into rock-hard ice. This means that agriculture, growing food locally, would be extraordinarily difficult. Soil, as we know it, does not exist. Nutrient cycles would have to be artificially created inside sealed habitats. Every element of survival would depend on technology. Air, water, food, heat, power, all would need to be produced and maintained continuously. A single failure in life support systems could become fatal within hours. This dependence on technology introduces another challenge. Maintenance. Machines wear out, components fail, materials degrade. On Earth, replacements can be manufactured and transported quickly. On Titan, spare parts would need to be carried in advance or manufactured locally using complex equipment, which means any long-term presence would require not just explorers, but entire industrial systems, factories, energy production facilities, recycling systems, all functioning reliably in one of the coldest environments in the solar system. And even if all of that were achieved, another problem remains. Gravity. Titan's gravity is only about 1/7 that of Earth. At first, this might seem appealing. Moving and lifting objects would be easier. But over long periods, low gravity causes serious health problems. Bone density decreases. Muscle mass weakens. The cardiovascular system adapts in ways that make returning to higher gravity difficult. Astronauts on the International Space Station experience these effects even after only months in microgravity. Countermeasures like exercise slow the process, but do not fully prevent it. No one has ever lived for years in low gravity. The long-term effects are still unknown. Now consider TRAPPIST-1e. Although it may have gravity similar to Earth's, its challenges are different, and in some ways even more severe. Because unlike Titan, TRAPPIST-1e orbits a red dwarf star. Red dwarfs are the most common type of star in the galaxy, but they are also unpredictable. They produce powerful stellar flares, releasing bursts of radiation that can be far stronger relative to the planet's distance than solar flares on Earth. These flares can strip away planetary atmospheres over time, leaving the surface exposed to intense radiation. Even if TRAPPIST-1e retains an atmosphere, radiation levels could still be dangerous, requiring habitats to be built underground or heavily shielded. And then there is tidal locking. Many planets in the habitable zones of red dwarfs are tidally locked, meaning one side always faces the star, while the other remains in darkness. If TRAPPIST-1e is tidally locked, one hemisphere could experience constant daylight and heat, while the other remains in permanent night and cold. The region between them, the twilight zone, might offer more moderate conditions, but winds driven by temperature differences could be extreme. Storm systems might be continuous, climate patterns unpredictable, surface conditions harsh and unstable. Even if life could survive in such environments, human infrastructure would face enormous stress. Then there is the question of ecosystems. On Earth, survival depends not only on air and water, but on complex biological cycles, microorganisms recycling nutrients, plants producing oxygen, and countless interactions maintaining balance. On another world, these systems would not exist. Human habitats would need to recreate entire ecological cycles artificially. Closed-loop life support systems have been tested on small scales, but maintaining them indefinitely without failure remains extremely difficult. A single imbalance in oxygen levels, microbial growth, or nutrient cycles could threaten an entire colony. Then comes another challenge, often overlooked: psychology. Living on a distant world would mean isolation, unlike anything humans have experienced. No open sky as we know it, no familiar landscapes, no easy return home. Communication delays would make real-time conversation with Earth impossible, especially for interstellar missions. Astronauts would need to cope with confinement, distance, and the knowledge that help is impossibly far away. Studies of long-duration missions in Antarctica and simulated Mars habitats show that psychological strain becomes one of the greatest challenges over time. Now imagine that strain lasting not months, but years, or a lifetime. Then there is the problem of children. If a permanent colony were established, families would eventually live there. But how would human development be affected by different gravity, radiation exposure, and artificial environments? No one knows. Human biology evolved under very specific conditions on Earth. Changing those conditions introduces risks that may not appear for generations. And finally, there is the question of sustainability. A colony that depends entirely on supplies from Earth is not truly independent. For Titan, resupply missions would take years. For TRAPPIST-1e, they would take decades or longer. Self-sufficiency would be essential. But building a self-sustaining civilization from scratch on a hostile world is one of the most difficult engineering challenges imaginable. And yet, despite all these obstacles, the dream of reaching other worlds persists, because exploration is part of human nature. But understanding the true difficulty of survival beyond Earth changes how we think about that dream. It reminds us that the universe is not waiting for us. It is not designed for us. It is a place of extremes, where survival requires preparation, patience, and humility. And perhaps that realization is not discouraging. Perhaps it is empowering, because before humanity can truly explore other worlds, we must first learn to preserve the one world that made exploration possible. And that realization leads to an even deeper question. If reaching Titan and TRAPPIST-1e is so difficult, what would it actually take to overcome these barriers? That is where the journey continues next. If humanity ever hopes to reach worlds like Titan or TRAPPIST-1e, the challenges cannot be solved by small improvements to existing technology. They would require changes so large that they would reshape how civilization produces energy, builds machines, and even thinks about time. Because at the heart of interplanetary and interstellar travel lies one fundamental requirement: energy. Moving a spacecraft across vast distances is not simply a matter of building a stronger engine. It is a matter of supplying enormous amounts of energy in a controlled and efficient way. Chemical rockets, the kind that launched Apollo astronauts to the moon and robotic probes to Mars, work by burning fuel. They are powerful but inefficient. Most of the mass of a rocket is fuel, and even that fuel provides only limited acceleration before it is exhausted. For journeys to nearby planets, this is acceptable. For journeys to Saturn, it becomes difficult. For journeys to another star, it becomes nearly impossible. To reach Titan in a reasonable time, perhaps a few years instead of a decade. Future spacecraft may need propulsion systems based on nuclear energy. Nuclear thermal propulsion, for example, uses a nuclear reactor to heat a propellant, which is then expelled to produce thrust. This method could double or triple efficiency compared to chemical rockets. Even more promising are nuclear electric propulsion systems, where reactors generate electricity to power ion engines. These engines provide low thrust but extremely high efficiency, allowing spacecraft to accelerate continuously over long periods. Such systems could shorten travel times significantly, but even nuclear propulsion has limits. To reach TRAPPIST-1e within a human lifetime, spacecraft would need to travel at a significant fraction of the speed of light, perhaps 10% or more. Achieving such speeds would require propulsion methods far beyond anything currently operational. Some concepts propose fusion engines, which would use the same process that powers the sun to produce thrust. Fusion contains enormous energy, but controlling it safely and efficiently remains one of the greatest engineering challenges ever attempted. Other ideas involve antimatter, which releases immense energy when it meets ordinary matter. In theory, antimatter propulsion could achieve extraordinary speeds, but antimatter is extremely difficult to produce and store. The total amount ever created on Earth is measured in tiny fractions of a gram. Producing enough to power a spacecraft would require energy and infrastructure far beyond current capabilities. Then there are even more speculative ideas. Light sails, for example, use powerful lasers to push extremely lightweight spacecraft using radiation pressure. Small probes could potentially reach nearby stars within decades, but scaling this concept to carry humans would require laser arrays of enormous size and power, along with sails kilometers across. And even if propulsion problems were solved, another barrier remains: shielding. At high speeds, interstellar space becomes dangerous. Dust particles, though tiny, carry enormous energy when collisions occur at tens of thousands of kilometers per second. A spacecraft traveling at 10% of light speed would need a protective shield capable of absorbing or deflecting these impacts without failing. Such shielding would add mass, which increases the energy required for acceleration, which increases the size and complexity of the propulsion system. Every solution introduces another challenge. Then there is the issue of navigation. Interstellar space is vast and mostly empty. A spacecraft traveling for decades or centuries must maintain precise orientation and trajectory. Small errors could grow into enormous deviations over time. Autonomous systems capable of detecting and correcting these errors would be essential, since real-time communication with Earth would be impossible. And communication itself becomes another challenge. Signals weaken with distance. A spacecraft traveling dozens of light years away would require powerful transmitters and enormous receiving antennas on Earth to exchange even small amounts of data. Messages would take decades to arrive. Explorers would operate in isolation, guided by instructions sent long ago, responding to a world that may have changed dramatically by the time their messages returned. Then comes the challenge of life support. Sustaining human life in space for years or decades requires closed-loop systems that recycle air, water, and nutrients continuously. These systems must be reliable, repairable, and efficient. On the International Space Station, many supplies are still delivered from Earth. For deep space missions, resupply would not be possible. Everything must work indefinitely. This requires not just engineering, but ecology. Artificial ecosystems capable of maintaining balance between oxygen production, carbon dioxide removal, waste recycling, and food production. Small-scale experiments have demonstrated parts of this concept, but creating a fully stable system for years or decades remains an unsolved problem. Then there is the question of gravity. Long-term exposure to microgravity weakens bones and muscles and alters circulation. Artificial gravity, created by rotating spacecraft sections, may provide a solution, but it introduces additional engineering complexity. Large rotating habitats would be required to simulate Earth-like gravity. These structures would need to be stable, safe, and durable over long periods. And then there is the problem of repair. In deep space, there are no rescue missions. Every system must be repairable using tools and materials available on board. Astronauts would need extensive training, not only in piloting and science, but in engineering, medicine, and fabrication. Spacecraft would need onboard manufacturing capabilities, possibly including 3D printing of components and materials processing. This transforms a spacecraft from a vehicle into a self-contained industrial environment. Then comes the deeper challenge of sustainability on arrival, reaching Titan or TRAPPIST-1e is only the beginning. Habitats must be built, power systems established, resources extracted, infrastructure created. On Titan, energy sources might include nuclear reactors or chemical processing of hydrocarbons in the atmosphere and lakes. On TRAPPIST-1e, the energy environment would depend on the star's brightness, atmospheric conditions, and local resources, unknown until detailed exploration becomes possible. Colonization requires not just survival, but production. Metals must be mined and processed, structures must be built, machines must be maintained. This means a colony must bring not only people, but the tools to create tools. And finally, there is time. Even with advanced propulsion, missions to distant worlds would take years or decades. Planning such missions requires political stability, long-term investment, and sustained public support. Civilizations must think not in years, but in generations. This may be one of the greatest challenges of all, because technology alone is not enough. Exploration on this scale requires patience, cooperation, and vision. It requires societies willing to invest in projects whose results may not be seen for decades. And that is not a technical challenge. It is a cultural one. Yet despite all these obstacles, progress continues. New propulsion concepts are studied, new materials are developed, new telescopes reveal distant worlds in greater detail. Humanity is still at the beginning of its journey into space. And perhaps the most important realization is this: reaching worlds like Titan and TRAPPIST-1e is not impossible forever, but it is impossible today. Understanding why is not discouraging. It is essential, because every great journey begins with understanding the limits that must be overcome. And beyond technology, beyond energy, beyond engineering, there remains another barrier, one that is more subtle, but just as powerful: the limits imposed by time itself. Beyond the challenges of propulsion, survival, and engineering, there is another barrier that shapes every attempt to reach distant worlds: time. Not just the time required to travel, but the way time itself changes in deep space, in the human bodies, and in civilizations. Time is often treated as something simple, a steady flow, measured by clocks and calendars. But in reality, time is one of the most complex and limiting aspects of space exploration. To understand why, it helps to begin with the most obvious effect: travel time. Even within our solar system, travel takes months or years. A mission to Mars can take 6 to 9 months using current technology. Reaching Saturn takes many years. During this time, astronauts are exposed to radiation, isolation, and the stresses of living in confined environments. Supplies must last. Systems must function reliably. Every additional day increases risk. For Titan, a human mission could take many years from departure to return. That means years spent in transit, years living in an alien environment, and years traveling back. Such missions would require astronauts to dedicate large portions of their lives to a single journey. And for TRAPPIST-1e, the time problem becomes far more severe. Even if a spacecraft could travel at 10% of the speed of light, a speed far beyond anything currently possible, the journey would still take hundreds of years. No human crew could survive such a trip without technologies that do not yet exist, such as long-term suspended animation. Some researchers have proposed generation ships, where multiple generations live and die aboard a spacecraft before reaching the destination. But this introduces profound social and ethical questions. Would future generations consent to a journey they did not choose? How would societies function in a closed environment for centuries? What happens if conflicts arise, or if the mission loses its purpose over time? A spacecraft carrying generations would not be just a vehicle. It would be a civilization in miniature. Maintaining stability under such conditions would be extraordinarily difficult, and even if a generation ship succeeded, those who arrived at TRAPPIST-1e would not be the same people who began the journey. They would be descendants, shaped by life in space, perhaps physically and culturally different from the humans who launched the mission. Then there is another aspect of time that few people consider: relativity. According to Einstein's theory of relativity, time does not pass at the same rate for all observers. As an object moves closer to the speed of light, time for that object slows relative to stationary observers. This effect has been measured with high precision using atomic clocks on fast-moving aircraft and satellites. At speeds achievable by today's spacecraft, the effect is tiny. But at a significant fraction of light speed, it becomes meaningful. Astronauts traveling near light speed could experience less time than people on Earth. In extreme cases, a journey lasting decades for travelers might correspond to centuries passing on Earth. This creates a strange and emotional consequence. Explorers who left Earth might return or send messages to a civilization that has changed beyond recognition. Languages may evolve. Nations may rise or fall. Technologies may transform society completely. Explorers would not only be traveling through space, they would be traveling into the future. And for interstellar missions lasting centuries, the gap becomes even greater. By the time a mission to TRAPPIST-1e arrived, the civilization that launched it might no longer exist in the same form. This raises a profound question. Who are such missions really for? The people who launch them, or the distant future? Then there is the time required not only for travel, but for preparation. Designing and building spacecraft capable of deep space missions takes decades. Testing systems, developing propulsion technologies, and ensuring reliability require patience and long-term investment. Space exploration operates on timescales far longer than most political or economic cycles. Governments change, budgets shift, priorities evolve. Sustaining a project for decades requires stability and cooperation, rarely achieved in human history, and yet some projects have succeeded. The Voyager spacecraft, launched in the 1970s, are still sending data today. Missions planned by one generation of scientists are completed by another. These achievements show that long-term thinking is possible, but interstellar travel would require thinking not just in decades, but in centuries. Then there is biological time. The human body ages, cells accumulate damage, muscles weaken, bones lose density. Even with advanced medical care, the human lifespan remains limited. For journeys lasting decades, astronauts would age significantly before reaching their destination. This affects mission planning, crew selection, and long-term health. Some scientists have proposed sending embryos or frozen genetic material instead of adult humans, allowing future generations to be born at the destination. But this introduces ethical and practical challenges that are difficult to resolve. Raising children in isolated, artificial environments without a broader society could have unpredictable psychological and social consequences. Then there is the time required to build a new world. Even if humans reached Titan or TRAPPIST-1e, creating a sustainable colony would take decades or centuries. Infrastructure must be built. Ecosystems must stabilize. Communities must grow. Colonization is not an event, it is a process, and processes require time measured in generations. Then comes another realization. Time also affects memory and meaning. The longer a mission lasts, the more distant its original purpose may feel. Cultural values change. Goals evolve. What seemed urgent at the beginning may seem less important later. Maintaining a shared sense of purpose over centuries may be one of the greatest challenges of all. Then there is the time required for science itself. Understanding distant worlds takes patience. Observations must be repeated. Data must be analyzed. Theories must be tested. The discovery of TRAPPIST-1e, for example, was not a sudden revelation. It was the result of years of observation, refinement, and collaboration. Science advances slowly, but steadily. And perhaps that slowness is not a weakness. It is a reflection of the universe itself, which unfolds over immense spans of time. Stars take millions of years to form. Galaxies evolve over billions of years. Planets cool and stabilize over epochs. Human timescales are brief in comparison. This contrast can feel discouraging, but it can also be inspiring because it reminds us that exploration is not only about reaching destinations. It is about participating in a long unfolding story, a story that began long before humanity existed and will continue long after. And perhaps the most important lesson of all is this: time is not merely an obstacle. It is a teacher. It teaches patience. It teaches humility. It teaches that some journeys cannot be rushed. Titan and TRAPPIST-1e are not unreachable because humanity lacks courage. They are unreachable because the universe operates on scales far larger than our everyday experience. Understanding those scales is the first step toward navigating them. And as we begin to understand the limits imposed by time, another realization begins to emerge. Distance and time are not the only barriers. There is also the environment of space itself, a place far more dangerous than it appears from the safety of Earth. That is where the journey leads next. Space often looks calm from a distance. When we see images of the night sky, it appears silent and still, stars fixed in place, planets moving slowly, darkness stretching in every direction. But this peaceful appearance hides a reality that is far more hostile than most people imagine. Between the worlds of the solar system, and even more so between the stars, space is one of the most dangerous environments known. And this danger is one of the main reasons why traveling to places like Titan or TRAPPIST-1e is so difficult. One of the greatest threats in deep space is radiation. On Earth, we are protected by two powerful shields, the atmosphere and the magnetic field. The atmosphere absorbs much of the high-energy radiation coming from space, while the magnetic field deflects charged particles from the Sun and from distant cosmic sources. In orbit, astronauts are already exposed to higher levels of radiation than people on Earth. Even on the International Space Station, which is still partly protected by Earth's magnetic field, radiation exposure is carefully monitored and limited. Beyond Earth's protective shield, radiation levels increase dramatically. There are two main sources of this radiation. The first is the Sun. Solar flares and coronal mass ejections release enormous bursts of energetic particles. These particles travel through space at high speed, and when they strike human tissue, they can damage DNA, increasing the risk of cancer and other diseases. During a powerful solar storm, radiation levels in deep space can become extremely dangerous in a short time. The second source is cosmic radiation from outside the solar system. These are high-energy particles accelerated by supernova explosions and other energetic processes across the galaxy. Cosmic rays are particularly difficult to shield against. They travel at extremely high speeds and can penetrate most materials, creating secondary radiation as they pass through spacecraft walls. For missions lasting months or years, radiation exposure becomes one of the most serious health risks. To protect astronauts, spacecraft would need heavy shielding, perhaps layers of water, specialized materials, or even magnetic fields designed to deflect charged particles. But shielding adds weight, and weight increases the energy required for launch and acceleration. Every solution introduces new challenges. Radiation is not the only danger. Micrometeoroids and interplanetary dust are constantly moving through space. These particles are usually tiny, often smaller than grains of sand, but they travel at enormous speeds. A collision with even a small particle can damage spacecraft surfaces, puncture equipment, or degrade protective layers. Spacecraft in Earth orbit already experience such impacts. For long-duration missions, especially those traveling at high speed, the risk increases. At interstellar velocities, even microscopic particles could release energy comparable to explosions. This means spacecraft must be designed not only for propulsion and life support, but for durability, able to withstand years or decades of exposure to impacts and radiation. Then there is the problem of temperature. Space is often described as cold, but the reality is more complicated. In direct sunlight, spacecraft surfaces can become extremely hot. In shadow, temperatures can drop to extremely low levels. Without an atmosphere to distribute heat, temperature differences can be severe. Spacecraft must manage heat carefully, using insulation, reflective coatings, and radiators to maintain stable internal conditions. Life support systems depend on precise temperature control. Electronics depend on it. Even structural materials can weaken or deform if temperatures fluctuate too much. Maintaining this balance over years in deep space is a complex engineering challenge. Another danger is vacuum itself. On Earth, atmospheric pressure surrounds us. In space, there is none. If a spacecraft hull were damaged, air would escape rapidly. A serious breach could become fatal in seconds. For this reason, spacecraft must be built with multiple layers of protection, redundant systems, and emergency procedures. And astronauts must always be prepared for the possibility of failure. Then there is the psychological environment of deep space. Unlike radiation or temperature, psychological stress is not visible, but it can be just as dangerous. Long-duration missions isolate astronauts from family, friends, and familiar surroundings. Communication delays prevent real-time conversation. The view outside the spacecraft may remain unchanged for months. Only darkness and distant stars. Monotony, confinement, and the awareness of distance can create stress, anxiety, and depression. Experiments in simulated space habitats have shown that even highly trained crews can experience tension and fatigue over time. Maintaining mental health in deep space would require careful planning, structured schedules, meaningful work, social interaction, and possibly new forms of psychological support. Then there is the risk of equipment failure. On Earth, if a system breaks, replacement parts can be delivered quickly. In deep space, repair must be immediate and self-sufficient. Every system must be designed with redundancy, backup components that can take over if one fails. But redundancy adds weight and complexity. And complexity introduces new points of failure. Balancing reliability, weight, and efficiency is one of the most difficult tasks in spacecraft design. Another challenge is communication. As spacecraft travel farther from Earth, signals become weaker and delays increase. At the distance of Saturn, signals take more than an hour to travel round trip. At the distance of TRAPPIST-1e, communication would take decades. Astronauts would need to operate independently, making critical decisions without immediate guidance from Earth. This requires training, autonomy, and trust in onboard systems. Then there is the issue of navigation. In deep space, there are no roads, no landmarks, no atmosphere to slow a spacecraft or provide aerodynamic control. Navigation depends on precise measurements of star positions, onboard sensors, and complex calculations. Small errors can accumulate over long distances, so guidance systems must be extremely accurate and reliable. Then comes a more subtle danger. Time and distance create a sense of separation not only physically, but emotionally. Explorers traveling far from Earth would know that returning home may never be possible. Even messages to loved ones would arrive years or decades later. This awareness could change how astronauts perceive their mission, their identity, and their connection to humanity. And yet, despite all these dangers, space exploration continues. Because understanding these risks is the first step toward overcoming them. Each mission teaches new lessons, Each spacecraft improves on the designs of those before it. Each generation of scientists and engineers moves a little closer to solving problems that once seemed impossible. And perhaps that is the most important realization. The dangers of space are real, but so is human ingenuity. Titan and TRAPPIST-1e remain beyond our reach today, not only because of distance and environment, but because space itself is a place that challenges every assumption about safety and survival. To travel there, humanity must learn not only how to move through space, but how to endure it. And as we begin to understand the dangers between worlds, another question naturally arises. If traveling to these places is so difficult and living there so challenging, why do we continue to dream of going at all? That is where the journey continues next. As the journey toward Proxima b stretches across imagination and science, another realization quietly emerges. Interstellar travel is not only a technological challenge, it is a test of civilization itself. Because to reach another star, humanity must first learn how to remain stable long enough to try. Now consider the fragile nature of human progress. History shows cycles, growth and collapse, innovation and conflict, expansion and contraction. Civilizations rise with great ambition, then fall under pressure. Interstellar projects require something rare in human history: continuity. Not just years, not just decades, but centuries of stable cooperation. This is difficult. Wars interrupt research. Economic crises cut funding. Political change reshapes priorities. Yet interstellar exploration cannot be paused and restarted easily. It demands sustained commitment, which means humanity must evolve culturally, not just technologically. Now consider the role of shared identity. When people see themselves primarily as members of nations, competition dominates. But interstellar exploration encourages a different identity: planetary identity, seeing humanity as one species on one world. Proxima b belongs to no flag, no border, no government. It is part of the universe, not a nation. To reach it, humanity must think beyond political divisions. Now, consider education again. Future generations will grow up in a world where nearby exoplanets are common knowledge. They will not see Proxima b as strange. They will see it as one of many neighboring worlds. This familiarity will shape ambition. It will normalize the idea that humanity is part of a larger cosmic neighborhood. This psychological shift is important because interstellar thinking begins in classrooms, not rocket labs. Now consider the role of storytelling. Stories shape motivation. If space exploration is told as conquest, it creates aggression. If it is told as discovery, it creates curiosity. If it is told as responsibility, it creates stewardship. Proxima b can be framed in many ways: as a prize, as a challenge, or as a lesson. Science favors the last interpretation. It is not a trophy, it is a case study. Now consider the emotional difference between proximity and reachability. Proxima b is close compared to other stars, but it is still unreachable with current human travel. This teaches a valuable lesson. Not everything that appears close is accessible. Distance in space is deceptive. What looks nearby in astronomical terms remains far in practical terms. This reminds humanity to be careful with assumptions. Now consider technological optimism. There is a belief that technology will eventually solve all problems, that faster engines will appear, that energy will become unlimited, that physics will be rewritten. While innovation is powerful, it is not unlimited. Some constraints may never be removed: speed of light, energy conservation, biological limits. These are not temporary obstacles. They are fundamental features of the universe. Proxima b forces humanity to confront this reality. Now consider adaptation. Instead of forcing the universe to change, humanity may need to adapt its expectations. Accept slower travel, accept robotic exploration, accept remote presence instead of physical presence. This is not failure. It is evolution. It is learning to work within cosmic limits. Now consider how this changes the idea of exploration itself. In the past, exploration meant movement, ships crossing oceans, astronauts walking on the moon. But future exploration may be about information, sensors instead of footsteps, data instead of territory, understanding instead of ownership. Proxima b fits into this new model. Now consider the emotional satisfaction of discovery. Seeing the first images of Proxima b, even from a fast flyby probe, would be historic. Not because humans arrived, but because humanity extended its perception beyond the solar system. This is a different kind of achievement, less physical, more intellectual, but equally meaningful. Now consider the long-term scientific value. Studying Proxima b will improve understanding of red dwarf star systems, atmospheric retention, radiation effects, planetary magnetic fields, climate stability. This knowledge applies to thousands of similar stars across the galaxy, which means Proxima b is not just one destination. It is representative of an entire class of worlds. Now consider the idea of stepping stones. Humanity rarely jumps directly to its largest goals. It moves step by step, from Earth orbit to the Moon, from the Moon to Mars, from Mars to robotic interstellar probes, from probes to more advanced missions. Proxima b is one of these stepping stones, not an endpoint. Now consider time once more. The universe is patient. Stars shine for billions of years. Galaxies evolve slowly. Human civilization is young. If humanity survives long enough, interstellar travel will feel less impossible. Not because physics changes, but because technology improves gradually. What seems impossible today may become routine centuries from now. But this requires continuity, which returns us to the central challenge: stability. Now consider the quiet responsibility that comes with this realization. If humanity wants to reach other stars, it must first protect its home, because without Earth, no interstellar future exists, no technology, no civilization, no curiosity. Proxima b indirectly reinforces this truth. It shows how fragile habitable conditions can be, how rare stable environments may be, how valuable Earth truly is. Now consider the emotional tone again. There is no urgency to rush toward Proxima b, no countdown, no deadline. The star will still be there, the planet will still orbit. What matters is whether humanity remains capable of exploration, which depends on choices made today. Now consider the role of cooperation. One last time. Interstellar projects require collaboration across cultures, across ideologies, across generations. They require trust, shared goals, common understanding. Proxima b becomes a unifying target, not because everyone wants to go there, but because everyone can participate in understanding it. Now consider the image of the future: a small probe leaving Earth, accelerated by lasers, crossing interstellar darkness. Years pass, decades pass, then data returns. Humanity gathers, scientists analyze, the world watches. This moment will not be loud. It will not be dramatic. It will be quiet. Screens showing faint images, graphs displaying atmospheric readings. But its significance will be enormous because it will mark the first true interstellar contact, not with aliens, but with another planetary environment. Now consider what happens after that. More missions, better probes, more targets. Interstellar exploration becomes routine, not common, but established. Humanity begins mapping nearby star systems, understanding galactic neighborhoods. This is the beginning of cosmic geography. Now consider the emotional meaning of this expansion. It does not make Earth smaller, it makes Earth more meaningful, because Earth becomes the reference point, the origin, the home. All exploration begins here. Now consider the final reflection of this part. Traveling to Proxima b is not about conquering distance. It is about learning patience, not about breaking physics, but about respecting it, not about escaping Earth, but about understanding the universe. And perhaps most importantly, it is about understanding humanity itself, its limits, its strengths, its potential, and its responsibility. Because the path to the stars does not begin with engines. It begins with values, with cooperation, with long-term thinking, with the decision to build a civilization capable of lasting long enough to explore beyond its birthplace. That decision is not made in space. It is made on Earth, every day, in classrooms, in laboratories, in policies, in choices, and whether humanity ever stands beneath the light of Proxima Centauri will depend less on speed and more on wisdom, and that quiet truth remains at the heart of this journey, not just to Proxima b, but toward the future of civilization itself. As the journey approaches its quiet horizon, Proxima b begins to feel less like a destination and more like a symbol of how far humanity has already come and how far it still has to go. Because when humans first learned that another Earth-sized planet orbited the closest star to the Sun, something shifted. The universe no longer felt unreachable, not because it became easy, but because it became personal. Proxima b is close enough to imagine, close enough to name, close enough to study in detail. And that closeness changes the relationship between humanity and the stars. Now consider what this does to imagination. For centuries, stars were distant lights, beautiful, untouchable, abstract. Now they are systems, with planets, with orbits, with environments. Proxima b transformed one small red star into a potential world. Not fantasy, not myth, but data. This is a profound shift, because imagination grounded in science becomes more powerful than imagination alone. Now consider how this affects hope. Hope is often misunderstood as optimism, as believing everything will work out. But scientific hope is different. It is the belief that understanding can grow, that knowledge can expand, that limits can be approached carefully. Proxima b represents this kind of hope, not the hope of instant arrival, but the hope of gradual progress. Now consider the idea of proximity again. 4 light years feels close on cosmic maps, but it remains far beyond everyday experience. This tension between closeness and distance mirrors many human goals. Some dreams feel near, yet require enormous effort. Proxima b teaches patience in ambition. It reminds humanity that meaningful goals are rarely quick. Now consider what happens emotionally when people realize how long interstellar travel takes. There is often disappointment, a sense of limitation, but there is also relief, because It removes unrealistic expectations. It grounds ambition in reality. It encourages long-term thinking rather than impulsive action. Now consider the relationship between science and humility. Science constantly reminds humanity that it is not central, not dominant, not special in position. Earth is not the center of the solar system. The sun is not the center of the galaxy. The galaxy is not the center of the universe. Proxima b continues this lesson. It shows that Earth-like planets may exist elsewhere, which reduces cosmic uniqueness, but increases responsibility. Because if environments are common but life is rare, then protecting life becomes more important. Now consider how this knowledge changes priorities. Interstellar dreams do not replace planetary needs, they highlight them. Because no spacecraft can leave Earth without Earth's resources. No civilization can explore the stars if it collapses at home. Proxima b indirectly demands planetary stability. It ties cosmic ambition to environmental responsibility. Now consider the quiet realization. The path to the stars does not begin with rockets. It begins with sustainable energy, with stable ecosystems, with education, with social cooperation, with long-term planning. Without these foundations, even the fastest engine is useless. Now consider the emotional effect of this understanding. It creates calm, not urgency, not panic, but clarity. Clarity about what matters first: Earth, then space. Now consider the difference between exploration and escape again. Some view space as a way to escape Earth's problems, but Proxima b shows that escape is not simple. It takes centuries, enormous energy, extreme effort. It is far easier to protect Earth than to replace it. This realization shifts motivation from running away to taking responsibility. Now consider the role of curiosity once more. Curiosity drives humans to explore even when there is no immediate reward. Proxima b offers no guaranteed benefit, no confirmed resources, no certainty of habitability. Yet it attracts attention, because curiosity is not based on utility alone. It is based on meaning, on the desire to know what exists beyond the familiar. Now consider the beauty of this drive. Humans look at a faint star in the southern sky, measure tiny fluctuations in light, discover a planet, and then spend years imagining how to reach it. This process is quiet, intellectual, patient. It does not involve spectacle, but it changes perspective. Now consider the future of interstellar thinking. As more nearby planets are discovered, humanity will build a mental map of its stellar neighborhood, not for travel, but for understanding. Which stars host planets? Which planets may have atmospheres? Which systems are stable? This creates a new layer of geography, not Earth geography, but cosmic geography. Proxima b becomes one of the first landmarks on this map. Now consider what this does to human identity. Humans will no longer think only as inhabitants of Earth. They will think as members of a star system, a local cluster of stars, a galaxy. This expanded identity does not erase national identity, but it adds another layer, a cosmic layer. Now consider how this may influence conflict. Seeing Earth as one planet among many can reduce the sense of absolute ownership. Borders become less significant. Resources become more shared. Perspective widens. This does not guarantee peace, but it encourages it. Now consider the emotional tone of this realization. There is something calming about knowing humanity is part of something larger, not isolated, not alone in structure. Even if life elsewhere is unconfirmed, the universe becomes a place of connection, not emptiness. Now consider the final role of Proxima b in this story. It is not the end of exploration. It is the beginning of interstellar awareness. The moment humanity realized that nearby stars are not just lights, but neighbors with worlds. This realization will not fade. It will grow stronger with each new discovery. Now imagine the far future, centuries from now. Humanity may look back at the early 21st century as the era when interstellar thinking truly began, when the first nearby Earth-sized planets were identified, when the first serious plans for interstellar probes were developed, when Proxima b became part of public awareness. It will be remembered not for arrival, but for awakening. Now consider the final calm image. Earth continues to orbit the Sun. Proxima Centauri continues to glow faintly. Proxima b continues its tight orbit, three bodies connected by gravity and distance, and between them, humanity's thoughts travel, ideas, plans, dreams, questions, not at the speed of light, but at the speed of curiosity. Now consider the closing truth. Traveling to Proxima b is not primarily about reaching another world. It is about learning to see this one differently, about understanding limits, about respecting time, about valuing stability, about recognizing responsibility. And in that sense, the journey has already begun. Not with engines, not with spacecraft, but with awareness. Awareness that the universe is vast, that Earth is fragile, that humanity is young, and that the path to the stars will be shaped not by speed, but by wisdom. And with that understanding, the story of Proxima b does not end. It rests quietly, waiting, like the star itself, patient, distant, unmoving, while humanity decides what kind of civilization it wants to become. Not tomorrow, not next year, but over generations, under this sky, on this planet, in this moment. And that choice is already in motion. As the final layer of this journey settles into silence, Proxima b no longer feels like a faraway object in space. It feels like a question about where humanity is going, and more importantly, how it will get there. Because when all the numbers fade, when the engines are imagined and the timelines are calculated, what remains is not speed, it is intention. Now consider the simple truth. Humanity does not yet have the technology to reach Proxima b quickly. It does not yet have the stability to maintain century-long missions easily. It does not yet have the global cooperation required for true interstellar projects. And yet, humanity continues to plan, to design, to imagine. This reveals something essential. Progress is not driven only by ability. It is driven by direction. Now consider the difference between movement and growth. Movement is physical. Rockets leaving Earth, probes crossing space, signals traveling through the void. Growth is internal. Knowledge expanding, perspective changing, values evolving. Proxima b contributes more to growth than movement. It changes how humanity thinks about space, not as empty darkness, but as a neighborhood of potential worlds. Now consider the emotional shift this creates. The stars become closer psychologically, not physically, but mentally. People begin to imagine nearby star systems as places with planets, with environments, with potential. This makes the universe feel alive, not empty. Now consider how this affects scientific curiosity. When something feels reachable, even if distant, curiosity intensifies. Proxima b is not one of thousands of anonymous stars. It has a name, an orbit, a story. This personalizes exploration. It gives humanity a focal point. Now consider the danger of impatience. Modern culture values speed, faster internet, faster transport, faster results. But the universe does not respond to impatience. Proxima b reminds humanity that some goals require waiting, decades, generations, long arcs of development. This teaches discipline, not the discipline of force, but the discipline of patience. Now consider the role of responsibility again. If humanity wants to reach other stars, it must first preserve the only platform capable of launching such missions: Earth. No amount of propulsion technology matters if ecosystems collapse. No interstellar dream survives environmental failure. Proxima b quietly reinforces this reality by showing how rare and delicate habitable conditions may be. Now consider the connection between interstellar ambition and planetary care. They are not separate goals. They are linked. A civilization that can stabilize its climate can plan long-term projects. A civilization that can cooperate globally can build interstellar infrastructure. A civilization that values science can pursue deep space exploration. Proxima b becomes a test of readiness, not technological readiness, but civilizational readiness. Now consider what kind of future humanity wants. One built on extraction and short-term profit, or one built on sustainability and long-term vision. Interstellar exploration favors the second path. It demands stability, trust, shared purpose. This is not guaranteed, but it is possible. Now consider the emotional calm that comes from accepting limits. There is relief in understanding that humanity does not need to rush to the stars. The universe will wait. Stars will continue to shine. Proxima b will continue to orbit. What matters is not speed, but direction. Now consider the idea of legacy again. People often think legacy is about monuments, achievements, recognition. But true legacy may be quieter. A stable planet passed to future generations. A civilization capable of cooperation. Knowledge preserved. Projects continued. Proxima b becomes part of this legacy thinking. It invites humanity to think beyond individual lifetimes, beyond personal achievement, toward collective progress. Now consider the emotional image one last time. A small probe leaving Earth, accelerated by light, traveling through darkness. Years pass, decades pass. It reaches another star. It sends back data. Humanity listens, not cheering wildly, but quietly absorbing new knowledge. This moment will not be dramatic in the traditional sense. It will be subtle, yet historically enormous, because it will mark the moment humanity became interstellar in awareness, if not in presence. Now consider the closing reflection. Traveling to Proxima b in 400 years or 15 days is not the real comparison. The real comparison is between fantasy and responsibility, between impatience and wisdom, between escape and understanding. Proxima b teaches that shortcuts are unlikely, but growth is inevitable. If humanity chooses it, now allow this thought to settle. The universe is vast, the stars are distant, the journey is long, but the path is clear, not through speed, but through stability, not through force, but through cooperation, not through escape, but through care. And in that sense, humanity has already begun traveling toward Proxima b, not with engines, but with ideas, with knowledge, with patience. and with the quiet decision to become a civilization capable of lasting long enough to touch the stars. Not today, not tomorrow, but someday. And that someday begins here, on Earth, under this sky, in this moment, where the future of interstellar travel is not written by technology alone, but by the choices humanity makes right now. And with that understanding, this journey gently comes to rest, not at Proxima b, but at the place where every great journey begins, home. As the final echoes of this journey continue to fade, one last layer of meaning quietly remains. Not about distance, not about speed, but about perspective, because Proxima b, in all its silence and distance, has already changed humanity, not by being reached, but by being imagined. Now consider how imagination shapes reality. Every major technological shift began as an idea. Flight began as observation of birds, satellites began as equations, space travel began as dreams written on paper. Proxima b now exists in this same mental space, a destination not yet reached, but already shaping design, research, and long-term planning. This is how futures are built, not suddenly, but gradually, through attention, through curiosity, through sustained interest. Now consider the importance of naming. Giving a world a name makes it real. Proxima b is no longer a catalogue number. It is a place in human thought. This changes how people relate to it. Names create connection. Connection creates motivation. Now consider how this affects younger generations. Children growing up today will learn about Proxima b in classrooms. They will not see it as exotic. They will see it as part of known space. This normalizes interstellar thinking. It prepares minds for long-term exploration. It plants seeds that may grow decades later. Now consider the idea of quiet milestones. Humanity often celebrates dramatic events, launches, landings, first footsteps. But some of the most important moments are quiet. Data analysis, scientific papers, gradual understanding. The discovery of Proxima b was such a moment. No explosion, no spectacle, just measurements, numbers, careful observation. Yet it shifted perception. Now consider the rhythm of science. Science moves slowly, carefully, methodically. This pace contrasts with public expectation. But it is necessary, because precision matters. Interstellar exploration cannot rely on assumptions. It requires accuracy. Now consider how this influences patience again. Proxima b teaches humanity to accept slow progress, to value careful planning, to trust incremental advancement. This mindset is valuable far beyond space. It applies to climate action, public health, education, social development. Interstellar thinking reinforces long-term responsibility. Now consider the emotional maturity required. Accepting that some dreams will not be fulfilled quickly is difficult. It requires emotional discipline, letting go of instant gratification. Proxima b demands this maturity. It invites humanity to grow psychologically, not just technologically. Now consider the quiet connection between all these themes: energy, environment, education, cooperation, time. They all intersect in the story of Proxima b. It is not just about a planet. It is about civilization design, how humanity organizes itself, what it values, what it prioritizes. Now consider the idea of cosmic humility one last time. The universe is vast. Human existence is small, but small does not mean insignificant. It means precious, fragile, worth protecting. Proxima b reinforces this by showing that Earth-like conditions may exist elsewhere. but they are not guaranteed. They are rare combinations of circumstances. This increases appreciation for Earth, not decreases it. Now consider the future again. Perhaps centuries from now, humanity will develop propulsion systems far beyond current capability. Perhaps fusion engines will become routine. Perhaps interstellar probes will be common. Perhaps human missions will become possible. Or perhaps humanity will remain largely confined to its local star system. Both outcomes are possible. Proxima b does not guarantee a specific future. It opens a path. What happens next depends on human choices. Now consider what kind of civilization humanity wants to be. One that consumes and expands without regard for limits, or one that grows carefully, responsibly, sustainably. Interstellar exploration favors the second. It demands planning, discipline, respect for resources. Now consider the quiet ending of this story. There is no final arrival, no landing, no flag planted on alien soil, because the true ending is not physical, it is mental, a shift in awareness, a change in how humanity views the universe, from distant and unreachable to structured and understandable, from mysterious and abstract to complex and knowable. Now consider the last image. Earth rotating slowly, clouds drifting, oceans reflecting sunlight, Proxima Centauri glowing faintly in the southern sky, Proxima b orbiting silently around its star. Three bodies connected not by travel, but by understanding, by knowledge, by shared curiosity. Now consider what remains after all calculations are done, after engines are designed, after timelines are drawn. What remains is purpose. Why explore? Why look outward? Why invest in long-term projects? Because understanding the universe helps humanity understand itself. Because curiosity is part of being human. Because looking beyond the horizon has always shaped civilization. Proxima b is simply the newest horizon. Now allow this thought to settle. The journey to Proxima b is not measured in kilometers. It is measured in years of research, in generations of learning, in cultural evolution, in cooperation. And that journey has already begun, not in space, but on Earth, in classrooms, in laboratories, in conversations, in choices. And as long as humanity continues to ask questions, to learn, to cooperate, to plan for the future, the path to the stars remains open, even if arrival is far away. And that is enough, because the value of the journey is not found only at the destination, but in what humanity becomes along the way. And with that understanding, this chapter of the story gently comes to rest, not with an ending, but with an open horizon, quiet, wide, waiting, just like the universe itself. As this journey reaches its final quiet depth, one truth becomes impossible to ignore. Proxima b was never only about distance, it was about direction. Because when humanity looks toward another star, it is not escaping its world, it is redefining its future. Now consider the idea of continuity. Civilizations that last are not defined by how fast they expand. They are defined by how well they preserve knowledge, how carefully they manage resources, how patiently they plan across generations. Interstellar ambition requires all three. Without continuity, no star will ever be reached. Proxima b becomes a reminder that survival comes before expansion, stability before movement, wisdom before speed. Now consider the relationship between science and responsibility. Science reveals what is possible. Responsibility decides what should be done. Just because humanity may one day develop powerful propulsion does not mean it should use it recklessly. Interstellar technology can bring discovery, but it can also bring risk. Radiation, energy misuse, environmental consequences, space debris, weaponization. Every technological leap carries consequences. Proxima b invites humanity to think carefully before acting. Now consider how this affects future generations. Children born today may never travel to another star, but they may help design the systems that allow future generations to try. Their contribution is not movement, it is preparation, education, innovation, stability. This is a quiet form of participation in interstellar history. Now consider the idea of collective effort. No individual will reach Proxima b alone. It will require thousands of scientists, engineers, technicians, teachers, policymakers, students, each contributing small pieces. Interstellar travel is not built by heroes. It is built by communities, by networks of knowledge, by cooperation across borders. Proxima b becomes a shared project, not owned by any one nation, but by humanity as a whole. Now consider the emotional maturity required for this level of cooperation. It requires trust, patience, tolerance, shared goals. These qualities are not guaranteed. They must be cultivated. Education systems, cultural values, media narratives, public understanding, all influence whether humanity becomes capable of long-term collaboration. Proxima b indirectly challenges society to improve these areas. Now consider the idea of cosmic responsibility. If humanity eventually reaches other star systems, it will carry its values with it, its ethics, its habits, its treatment of environments, its respect for life. Interstellar expansion without responsibility risks repeating old mistakes on a larger scale. Proxima b offers a chance to design a better approach from the beginning, one based on study, respect, minimal interference, scientific observation rather than exploitation. Now consider how this aligns with modern planetary protection policies. Space agencies already avoid contaminating other worlds. They sterilize spacecraft. They follow strict protocols. This shows awareness that exploration carries ethical responsibility. Interstellar exploration will amplify this challenge because consequences become irreversible across light years. Now consider the emotional image again, a probe traveling silently through interstellar darkness. No crew, no voices, just sensors and code, carrying humanity's curiosity. This image is powerful because it is humble. It does not dominate space. It simply observes, learns, reports. This is the most realistic model of early interstellar exploration, not conquest, but observation. Now consider what happens when humanity receives the first close data from Proxima b. There will be excitement, but also reflection. What does this information mean? How should it be used? Should humanity plan human missions or remain focused on robotic exploration? Should resources be invested in propulsion research or environmental stability first? These questions will shape future policy. Now consider how Proxima b may change scientific priorities. Exoplanet research will become more targeted. Atmospheric spectroscopy, magnetic field detection, surface modeling, climate simulation. These tools will improve not only for Proxima b, but for thousands of other worlds. This expands humanity's understanding of planetary diversity, which helps answer fundamental questions. How common are Earth-like planets? How stable are habitable environments? How rare is life? Proxima b contributes to this broader picture. Now consider the psychological shift again when humanity realizes that potentially habitable planets exist nearby. Earth no longer feels isolated. This can create two opposite reactions: carelessness or appreciation. One reaction leads to neglect, the other leads to protection. Science increasingly promotes the second, because while planets may be common, life-supporting conditions may not be. Earth remains unique in confirmed life. Now consider the deeper emotional truth. Proxima b does not replace Earth. It highlights Earth's value. It reminds humanity that even if other worlds exist, none are guaranteed safe. None are guaranteed accessible. Earth remains home, not temporarily, but fundamentally. Now consider how this realization changes long-term planning. Instead of focusing only on escape strategies, humanity may focus on sustainability, renewable energy, environmental restoration, population stability, education, global cooperation. These are prerequisites for any serious interstellar future. Proxima b indirectly encourages these priorities. Now consider the quiet irony. The more humanity looks outward, the more it is forced to look inward. Interstellar ambition becomes a mirror, reflecting weaknesses, highlighting strengths, exposing areas that need growth. This is the real value of distant worlds, not the worlds themselves, but what they reveal about humanity. Now consider the final emotional tone. There is no urgency to rush, no pressure to arrive tomorrow. The universe is patient. Stars live long. Planets orbit endlessly. Humanity has time, if it chooses stability. Now consider the final image of this part. Night falls on Earth. Cities glow softly. Satellites pass overhead. Somewhere far away, Proxima Centauri shines faintly. Invisible to most people, yet present, waiting. Not for humans, but for understanding. Now consider the quiet promise. If humanity continues to learn, to cooperate, to care for its planet, to invest in science, then one day, perhaps centuries from now, a new generation may look back at this era and say, this was when interstellar civilization began, not with engines, but with awareness, not with speed, but with responsibility, not with conquest, but with curiosity. And that is where this story truly belongs. Not in the future, not on another planet, but in the present, in the decisions humanity makes today. Because every choice shapes the path forward, every policy influences stability, every scientific investment builds capability, every educational effort grows understanding. And through these small, quiet actions, the journey to Proxima b continues, not through space, but through time, through culture, through progress, through wisdom. And as long as humanity continues to choose cooperation over conflict, knowledge over ignorance, responsibility over recklessness, the stars will remain open, not as destinations to conquer, but as mysteries to understand. And with that realization, this chapter of the journey gently fades, not with an ending, but with a calm horizon. A horizon not made of light years, but of possibility, waiting, silent, patient, just like the universe itself. In the end, the story of worlds like Titan and TRAPPIST-1e is not only about distance, technology, or the limits of physics. It is about perspective. Because when we look at these distant places, frozen moons beneath orange skies, rocky planets circling dim stars, we are not only seeing other worlds, we are seeing the scale of the universe itself. And that scale changes how we think about everything. For most of human history, the world felt vast. Oceans seemed endless, mountains insurmountable, deserts impossible to cross. But over time, exploration revealed that Earth, though large, is finite. Space is different. Space does not end where the horizon meets the sky. It stretches outward in all directions, farther than imagination can easily follow. Distances are measured in light years. Timescales are measured in millions or billions of years. In such a universe, the journey to Titan, years long, becomes a short trip. The distance to TRAPPIST-1e, 40 light years, becomes a nearby destination compared to the thousands of light years across our galaxy. And yet, even these immense scales are only a small part of the observable universe. This realization can feel overwhelming at first. It can make humanity seem small, fragile, almost insignificant. But there is another way to see it. In a universe so vast, the emergence of life, of consciousness, capable of asking questions, is extraordinary. The atoms that make up human bodies were forged in ancient stars. The oxygen we breathe, the carbon in our cells, the iron in our blood all originated in stellar explosions billions of years ago. We are not separate from the universe. We are made of it. This means that when we study space, we are not studying something foreign. We are studying our own origins. Titan's chemistry may resemble the early Earth that eventually gave rise to life. TRAPPIST-1e may represent one of countless worlds where conditions might allow biology to emerge. These places are not only destinations. They are clues about how planets form, how atmospheres evolve, how life begins, and how fragile the conditions for life truly are. And perhaps the most important lesson of all is this: Earth is rare, not necessarily unique, but rare. Liquid water, a stable climate, a protective magnetic field, and an atmosphere rich in oxygen are not common combinations. The more we learn about other worlds, the more we understand how many things had to align for life to flourish here. This realization does not diminish the dream of exploration. It strengthens the responsibility to protect the world we already have, because reaching Titan or TRAPPIST-1e will never be easier than preserving Earth. Another lesson emerges from considering the limits of travel. For centuries, humans believed that with enough determination, any destination could be reached. Oceans were crossed, mountains were climbed, the sky itself was conquered. But space introduces limits that are not easily overcome. The speed of light is not just a technical barrier. It is woven into the structure of reality. Time itself becomes a factor in ways that no earlier explorers ever faced. These limits do not end exploration. They reshape it. They remind us that the universe is not something to conquer. It is something to understand. Understanding is slower than conquest, but it is deeper. Then there is the realization that exploration is not only physical. Telescopes allow us to study worlds we may never visit. Spectroscopy reveals the composition of distant atmospheres. Mathematical models allow us to simulate climates, oceans, and even the formation of galaxies. Knowledge travels where spacecraft cannot, and knowledge has its own power. It changes how we see the world. It changes how we see ourselves. The first images of Earth from space changed how many people thought about the planet. Borders disappeared. The atmosphere appeared as a thin, fragile line. The planet looked small and alone in the darkness. That image, often called the pale blue dot perspective, remains one of the most powerful lessons of space exploration. It reminds us that everything we have ever known exists on a single world. Every city, every language, every story, all within a thin layer of air on a small planet orbiting an ordinary star. When we think about traveling to Titan or TRAPPIST-1e, we are really thinking about leaving that small, fragile world. And that thought carries both excitement and responsibility. Because exploration is not only about reaching new places, it is about deciding what kind of civilization we want to become. A civilization that cooperates, shares knowledge, and plans for the future has a chance to endure. A civilization that ignores its limits may not. The universe does not guarantee success, but it offers opportunity. Opportunity to learn, to discover, to understand. And perhaps that is enough, because the true value of exploration is not measured in kilometers traveled or planets reached. It is measured in understanding gained, in perspective gained, in the quiet realization that we are part of something far larger than ourselves. Titan and TRAPPIST-1e may remain beyond our reach for generations, but they have already changed us. They have expanded the boundaries of imagination. They have challenged assumptions about what is possible. They have reminded us that the universe is vast and that our journey has only begun. And perhaps the most profound realization of all is this: the universe is not waiting for us. It is not designed for us, but it allows us to exist, to think, to wonder, to ask questions that echo across space and time. And as long as those questions continue, exploration continues, not only outward toward distant worlds, but inward toward a deeper understanding of what it means to be human in a universe that is vast, silent, and endlessly fascinating. The journey to Titan and TRAPPIST-1e may still lie far in the future, but the journey of understanding is already underway, and that journey may be the most important one of all.